Hello, you curious minds and future shapers, and welcome back to the channel. Take a look at the device you're watching this on. Your smartphone, your laptop, your smart TV, they are all modern marvels of engineering, built on a principle that's powered our digital world for nearly a century: the bit. A simple, reliable switch that is either a 0 or a 1, off or on. It's a binary system that has allowed us to build empires of information, connect the globe, and put supercomputers in our pockets. But what if I told you that this foundation, as powerful as it is, has a fundamental limit? What if there are problems so colossal, so complex, that even a supercomputer the size of a planet, running for the entire age of the universe, couldn't solve them? These problems exist, and they hold the keys to curing diseases, reversing climate change, and understanding the very fabric of reality. To solve them, we don't just need a faster computer, we need a completely new kind of computer. Welcome to the dawn of the quantum age. So what exactly is quantum computing? To understand it, we have to throw out the rule book of classical computing. Instead of bits, a quantum computer uses qubits, and this is where things get mind-bending. Thanks to a principle called superposition, a qubit doesn't have to be just a 0 or a 1. It can be a 0, a 1, or... Imagine a classical bit is a light switch. It's either on or off. A qubit, however, is like a spinning coin. While it's in the air, spinning, it's not definitively heads or tails. It's in a probabilistic state of being both. It's only when we measure it, when the coin lands, that it collapses into a definite state of either heads, 0, or tails. This ability to exist in multiple states at once is the first secret to a quantum computer's power. With just 2 classical bits, you can represent one of 4 possible combinations: 0, 0, 0, 1, 1, 0, or 1, 1, at any single moment. But with 2 qubits in superposition, you can represent all 4 of those combinations. Add a 3rd qubit and you can represent 8 states, a 4th, 16. This power grows exponentially. With just 300 qubits, a quantum computer could represent more possible states than there are atoms in the known universe. This isn't just an upgrade, it's a paradigm shift in how we process information. It allows a quantum computer to explore a vast landscape of solutions all at once instead of checking them one by one like a classical computer. But that's only half of the magic formula. The second key principle is arguably even stranger, a phenomenon Einstein famously called spooky action at a distance. It's called entanglement. When 2 qubits become entangled, their fates are intrinsically linked, no matter how far apart they are. They become a single unified system. If you measure 1 qubit and find it's a 0, you instantly know, without measuring it, that its entangled partner is a 1. It's like having a pair of magic gloves. You put them in 2 separate boxes and mail one to the other side of the universe. The moment you open your box and see a left-handed glove, you know faster than the speed of light that the other box contains a right-handed glove. This interconnectedness allows for incredibly complex and powerful correlations between qubits, creating computational shortcuts that are impossible in the classical world. It's this beautiful, strange dance between superposition and entanglement that gives quantum computing its revolutionary potential. So where are we today? Is this technology still confined to university blackboards? Absolutely not. We are currently in what's called the NISQ era, noisy intermediate scale quantum. Tech giants like Google, IBM, and Microsoft, along with innovative startups like Rigetti and IonQ, are in a fierce race to build more powerful and stable quantum processors. You might have heard of Google claiming quantum supremacy, or IBM putting their quantum computers on the cloud for researchers to use. We're now dealing with machines that have dozens or even hundreds of qubits. However, noisy is the key word here. The quantum world is incredibly fragile. The slightest vibration, a tiny change in temperature, or a stray magnetic field can cause a qubit to lose its quantum state, a process called decoherence. It's like that spinning coin getting bumped before it can land naturally. This is why quantum computers are often housed in massive chandelier-like supercoolers called cryostats, kept at temperatures colder than deep space to protect the delicate qubits from the noise of the outside world. On top of decoherence, quantum calculations are prone to errors. Developing robust quantum error correction is one of the biggest hurdles in the field. It might take thousands of noisy physical qubits just to create a single, stable, and reliable logical qubit. So while we're not going to have a quantum laptop anytime soon, the progress is breathtaking, and the potential applications are what drive this multi-billion-dollar race. Let's talk about that potential. In medicine and drug discovery, designing a new drug involves understanding how complex molecules like proteins will interact with it. For a classical computer, accurately simulating these interactions is an impossible task. But a quantum computer, operating on the same quantum mechanical principles as the molecules themselves, could simulate them perfectly. This could slash the time it takes to develop new life-saving drugs from a decade to a matter of months, leading to personalized treatments for cancer or cures for diseases like Alzheimer's and Parkinson's. In material science, we could design revolutionary new materials from the ground up. Imagine creating a room-temperature superconductor, which would lead to lossless energy grids, hyper-fast levitating trains, and incredibly powerful magnets for medical imaging. Or designing a new catalyst that pulls carbon dioxide out of the atmosphere with perfect efficiency. Or a battery that's 10 times more powerful and charges in seconds. Quantum computers could unlock a new era of manufacturing and green technology. Then there's the double-edged sword of cryptography. The very encryption that protects our bank accounts, government secrets, and online data, known as RSA encryption, is based on the fact that it's incredibly difficult for classical computers to factor large numbers. For a quantum computer running Shor's algorithm, it's a trivial task. This means that a powerful quantum computer could, in theory, break most of the encryption we rely on today. But the quantum world also provides a solution: quantum cryptography. Technologies like quantum key distribution, QKD, use the principles of quantum mechanics to create unbreakable communication channels. If a third party tries to eavesdrop, the very act of measuring the quantum state disturbs it, alerting the sender and receiver instantly. Finally, in artificial intelligence and optimization, quantum computing could supercharge machine learning. It could solve incredibly complex optimization problems that are currently out of reach, like optimizing global supply chains in real time to respond to a crisis, creating financial models that can accurately predict market crashes, or developing far more sophisticated and powerful AI systems. The road to a fault-tolerant, universal quantum computer is long and filled with immense scientific and engineering challenges. We are at the very beginning of this revolution, much like the pioneers of classical computing were in the 1950s with their room-sized machines. But the destination is not just a faster computer, it's a new tool for understanding the universe and a key to unlocking a future that today we can only dream of. It's a technology that will redefine what is possible. Thank you so much for joining us on this deep dive into the mind-bending world of quantum computing. What potential application excites you the most? Let us know down in the comments. If you found this as fascinating as we did, please hit that like button and be sure to subscribe and ring the bell so you don't miss our next exploration into the tech that is shaping our future. Until next time, stay curious.